Good evening. In the last speech of this session, I've been entrusted with the task of presenting to you the tools that any winery has at its disposal in order to resolve or prevent light struck defects or light-related problems. In other words, I'll be summarizing what the previous speakers have already described, the origin and characteristics of the light-struck taste, if there are any predictive factors, and how widespread, how prevalent the problem is. And part of my presentation will also take into consideration the steps in the process where a direct action by the winemaker might avert the problem occurring to the detriment of riboflavin or riboflavin, and then to reduce the problem substances during the fining process, and then evaluating if it is possible to use substances or adjuvants that will exert a protective action vis-à-vis the defect during bottling or just before bottling. I'll briefly summarize what has been mentioned before. The light-struck taste is a defect that tends to occur in wines when they are exposed to light radiations comprised between 370 and 450 nanometers on average. And for this problem to occur in the wine, there must be photosensitive precursors, primarily riboflavin, which reduces and therefore will lose color, become colorless, and components that can provide electrons to riboflavin. And so basically the presence of sulfurated amino acids or methionine that can release components creating DMDS, mercaptan, and other problem substances. What are the sensory effects of this problem? Well, that will primarily affect the flavor and the color of the wine. The odor of the wine also, for instance, the typical off odors of garlic, cabbage, and onion, and also the loss of freshness and fruit. The color will suffer from two opposite effects. Initially, there might be a loss of the color intensity in the wine due to the reduction in riboflavin, and then later the so-called browning might occur due to the collateral reactions which will accompany the reduction in riboflavin, that is oxidation in the wine, that might lead to the oxidation of cinnamic acids and polyphenols more generally, such as catechins. Let's now look at the incidence of this defect in bottled wines. Obviously, bottles must be see-through to allow light radiations originating the defect to enter through the glass wall. Particularly, the wines involved are still white wines, rosés, and sparkling wines in white bottles. It is a well-known fact and a well-demonstrated fact that the phenomenon hardly ever occurs in red wines, because certainly there is a protection offered by the high content in polyphenols in the red wines, which screen off, that fend off the light radiations that are so damageful. In the literature, you find many studies that attempted to connect the incidence of this phenomenon with the grape variety that it tends to affect. The neutral varieties seem to be more sensitive to the problem because the aromatic varieties, because of the aroma of the wine, will mask the problem and or will interact with the sulfur-containing compounds that are formed. Other predictive factors are the tannins and amino acids in the wine, because apparently the prevalence of sulfur-based amino acids, which are precursors of mercaptans, can have a negative influence, thus increasing the light-struck taste effect. And then the content of riboflavin, which might be characteristic of given varieties. I would also like to highlight possible criticalities in connection with this defect. That is the fact that consumers don't always identify the problem. Very often they associate it to a bad quality of the wine itself and not to improper storage of the wine. So the consumer will feel that the wine is of poor quality when it isn't. Unlike the corkiness of the wine, which is also reflected in the fact that the consumer is not buying that wine again, but without providing reasons, without providing a feedback. Now, a couple of words now on riboflavin, which is the key element in this defect. Riboflavin is contained in wines in the order of a few hundred ppbs. As a maximum, you will find 400 ppbs. You can find it in the grapes and in the must, but the largest amounts are produced by the yeast during the alcoholic fermentation. Why is the concentration in riboflavin so critical? It's because it is the limiting factor. The methionine can be found in must and wines in much higher concentrations in terms of a few ppms, whereas riboflavin has much lower concentrations, parts per billion. Now, in the literature, it has been proven that there is a safety threshold for riboflavin below which the defect is hard to perceive, and that safety threshold is anywhere between 80 and 100 ppbs. In the model solutions in the tests that Jordan Sinas has shown to you, the defect was perceivable even at lower riboflavin concentrations, down to 50 ppbs. But this should not come as a surprise because the model solution is not wine. And the compounds that are present in the model solution, in the sample solution, are a lot less numerous than in wine, whereas with riboflavin in real wine you have other substances that can react and thus sort of interact with the methionine as well. Let's now assess the 4 significant steps in the winemaking process during which it is certainly effective to take action in order to eliminate or even avert the problem. The first 2 have to do with alcoholic fermentation. First of all, the yeast strain is important because different yeast strains will result in different riboflavin production. The second has to do with the addition of nutrients and to the fermentation conditions. The first 2 steps, again, are pertain to the production of riboflavin. Now, when it comes to fining, we shall see in a moment how, adding different adjuvants, it is possible to reduce also to a large extent the riboflavin content in wine, and then we'll see what added substances can do in order to improve protection just before bottling the wine. Here, I'm summarizing the ppb of riboflavin produced at the end of an alcoholic fermentation on a Chardonnay must. As you can see, a variation is large. In particular, we have identified 2 yeast strains. The first is a Saccharomyces cerevisiae, fervens fragrans, which on top of being one that has very good winemaking properties and with a high aroma production, produces riboflavin to an extent of less than 30 ppbs. A second yeast strain, which has not been marketed yet,
is Saccharomyces baianus. This strain is particularly relevant for spumante making, particularly second fermentation, because alcoholic fermentation for wines that take bottle fermentation is essential, because spumante or sparkling wines in general will not be fined, and therefore there are fewer opportunities, fewer options to reduce a riboflavin content once it's been produced. So it's very important, in other words, to take action during alcoholic fermentation. Now let's look at other factors that can influence the production of riboflavin. Fermenting temperature, when it's low, low fermentation speed, and the low number of live cells. All three generally will lead to lower riboflavin production. What we investigated was whether the presence of precursors of the light struck taste in the nutrients could have an influence on the final content of riboflavin in the wine. As we ascertained, if we feed the yeast only based on ammonia salts or yeast derivatives with yeast derivatives added to it that contained approximately 70 ppm of riboflavin, riboflavin at the end of the alcoholic fermentation was higher in the second sample, so with an extra riboflavin content by 20 to 30 ppbs. This is not a very high number, but it can have an impact, particularly if you have reached the safety threshold for riboflavin already. So in this case, the fermentation was very similar in terms of pattern for both samples, in terms of speed of fermentation and number of live cells and temperature. Dal Cin has two nutrients in its range that have a low riboflavin content, known as winterful and fructol. Winterful is a complex nutrient and a complete one that contains both ammonia salts and organic substance. On top of a rich vitamin pool, it also ensures survival factors such as magnesium, together with other oligo elements. But the most relevant thing is the production form or format, which is the mini tubes, which are easy to use and that are very easy to store and handle, which are were very nicely welcomed by the consumers. Fructol is exclusively nitrogen, organic nitrogen, on top of low riboflavin content. It has a rich vitamin pool, as well as amino acids, which is ideal for fruity aromas. Another step that we investigated was that of fining. In this chart, I have represented some of the tests that we carried out on the model solution using different fining adjuvants or agents. So this is the residual riboflavin as a percentage. Silica actually didn't act a lot. Bentonite at different doses showed different levels of action in terms of riboflavin absorption. PVPP up to 80 grams per hectoliter did not bring about any particular action. We then tested kaolin and zeolite, which is a relatively good absorbent, and then some protein-based fining agents such as egg whites, and then different types of carbons which reduced to a different extent the riboflavin content depending on their origin and activation characteristics. We took good care to identify the products that had the most significant effect in terms of riboflavin reduction, preserving as much as possible the sensory characteristics of the wine.
We therefore developed a specific fining agent which is characterized by a dramatic reduction in riboflavin content, and on top of that it also makes it possible to improve the quality of color by acting on color compounds that are or might be oxidized. And also the packaging, the format is many tubes. A correct management of alcohol fermentation, by the way, will also make it possible to use this adjuvant at low dosages with an negligible impact from a sensory perspective. Let's now look at some tests that we've carried out on wines using this fining agent. In this case, we have a Pinot Gris, which had a riboflavin content equal to 170 ppbs. We used growing doses of the fining agent, 5, 10, and 30 grams respectively. At 10 grams per hectoliter of the fining agent, you already go below the safety threshold for riboflavin in wine. Obviously, if the wine contains 440 ppbs of riboflavin, it's going to be much harder to lower the riboflavin content below the acceptable threshold, and certainly we won't be able to eliminate riboflavin completely. This is the effect that it has onto color at different concentrations. Larger fining agent concentrations will affect the color much more, but will also help us prevent color browning. And then, finally, one last test. We tried to taste the wines treated before irradiation, irradiating them always with an instrument, with a tool that made it possible to completely degrade riboflavin after irradiation. It's interesting to notice that the panel members did not detect any statistically significant differences on the three wines: the untreated wine treated with 10 grams per hectoliter of fining agent and 30 grams per hectoliter of fining agent. Now, the picture was immediately and clearly different after irradiation. Actually, in this case, the wines that were treated were preferred over the untreated wine that was where the light-struck taste defect was very evident, whereas the wines below the safe riboflavin threshold didn't display any such defect.
Let's now consider pre-bottling protection. How can you protect wine against this defect from the very beginning? Basically, you have three mechanisms. First, you cover, in a way, the light source. You supply it with substances that can interact with riboflavin instead of sulfur precursors, or you eliminate metabolites which have formed. We tested antioxidants, amino acids, metals, such as copper and silver, and tannins. In order to perform the test, as a matter of fact, we first had a test on the model solution, and then we tested wine. I will show to you only the wine tests, in this case a Chardonnay with 174 ppb of riboflavin. A number of wine bottles were added with potential protectors of wine, and then irradiated. An untreated bottle was kept away from light, and an untreated bottle was radiated with light. Then panelists were asked to give a zero defect to the non-radiated wine, and 10 where the radiation had occurred completely. This is the average of the score in terms of intensity of the defect which was found. Specifically, you can see here SO2, which has a weak protective effect, while ascorbic acid had a major protective effect, while at the same time we also need to remember that you should add further things in order to avoid oxidation. The acid did not entail major advantages, while the result obtained with silver chloride on bentonite was extremely interesting. This is what was obtained in the same type of test when adding different types of tannins. Specifically, the best performers was one of these tannins in a combination with the SO2 in a reduced form, therefore. That probably acted as both antioxidant and as potential molecule binding volatile thiols and smelly substances in this case. What we did was to convey all information and knowledge acquired into one product, which we called REDOX longevity, which prevents fast organoleptic degradation of wine. It acts exploiting both preventive and curative mechanisms. In this case, you see here evidence of its efficiency in preserving the various characteristics of the Chardonnay wine. I would like to conclude by showing to you this overview of instruments which are available to wineries. Please remember that at our stand you can taste wines where there is the light struct taste defect. I would like to thank Professor Tirelli from Milan University for his precious scientific support and contribution in supporting Dr. Encina's work. Thank you very much.